Okay, so first of all, I thank the organizers for inviting me to give this talk here today. And so my talk is about the quantum gravitational correction to the entropy of a Reissner-Nordström black hole. And it is based on this paper, which contains actually some typos. So I will upload soon an updated version with the corrections. Okay, so first I will give an introduction about some facts on quantum gravity. Then I will proceed to compute the quantum gravitational correction to the Reissner-Nordström metric. And then I will compute the gravitational correction to the entropy. And then at the end we will have a look at possible future directions. Okay, so let's start with the introduction. So as everyone knows, one of the greatest achievements in theoretical physics in the past years is the discovery that black holes have an entropy. And this was first discovered by works of Bekenstein and Hawking in the 70s. But now the question is, how do we actually compute the entropy of black holes? And there are several methods. In this work, we use the Wald approach. So in the 80s, Wald, he derived this formula for computing the entropy of black holes. So here, L is the Lagrangian of the theory, and RH is the horizon radius, and then R mu nu rho sigma is the Riemann tensor, and epsilon mu nu is some antisymmetric tensor, totally antisymmetric tensor normalized as epsilon mu nu equal to -2. Okay, so but what is L? So which theory of quantum gravity are we actually using? So a possibility is is using an effective field theory approach. And this was first done by Russian scientists, Barvinsky and Wilkowinsky, in the 80s. So the idea is to start from general relativity and to integrate out the massless fluctuations. So in the end we get an effective action, which contains two terms. First, we have a local Lagrangian, namely this one, which is an expansion in terms of the curvature. So this Lagrangian is up to order 2 in the curvature. So as you can see here we have R squared, and then R mu nu, and then this other term. And if I could also go ahead and to the third order, and I would have R to the power 3 and so on. But up to second order, then this is the action. And then we have a known local action, which is the following. And it is non-local because it contains this object. So it is logarithm of box divided by mu squared, where the box here is the D'Alembert operator, and mu is an arbitrary energy scale. And with this operator we are acting on R, R mu nu, and so on. So due to the presence of the logarithm, this action is non-local. Now we want to derive the equation of motions from this action, since, as I said before, this is the usual Einstein-Hilbert action, but then here we have other additional terms. So the equation of motions will be the usual Einstein equations, but then we will have some additional quantum corrections. So the solution of this, it will be a metric, which is written in terms of some classical metric, plus some quantum corrections. Now, there is an important point here. The quantum correction to the metric imply a shift to the horizon radius of the black hole. And since the Wald formula requires to integrate over the event horizon, then it is very important to first find the quantum correction to the metric before proceeding to compute the entropy. So first I have to find the new position of the event horizon, and then I can apply the Wald formula to find the entropy. With this approach, so far, only Schwarzschild black holes have been studied. So it is remarkable to say that even though the Wald formula was found in the 80s, only last year, so in 2021, Calmet found used this approach to find the quantum corrections to the entropy of a Schwarzschild black hole. And this is the result that he found. And now, in this research, we want to go beyond Schwarzschild black hole. We want to generalize these calculations. And the easiest generalization that we can do is studying an electrically charged black hole, namely a black hole also called Reissner-Nordström. So this black hole has an electric charge. So it's different from the previous case, where we had only Schwarzschild. Here we have a charge, so that we are not anymore in vacuum, but the black hole generates an electromagnetic field. So the energy momentum tensor is not anymore at zero. Okay, so how do we compute the corrections to the metric, to the classical Rn metric? So first, since we are considering an electrically charged black hole, to the purely gravitational terms, we have to add the Maxwell action, where, as usual, F nu is the electromagnetic tensor, and A nu is the connection for electromagnetism. So F nu is equal to del nu a nu minus the nu a nu. So the full action is then the sum of all the local action, gravitational local action, plus the non-local action, plus the action due to Maxwell, the Maxwell action. And we take the derivation of the action with respect to g nu and the nu, and this gives the quantum corrected Einstein and Maxwell equations respectively. But before proceeding, we have to address an important point. So, as I said before, the no-local action contains a logarithm. And so what is exactly this logarithm? How do we compute the action of that logarithm on a certain function? As it was shown in 2019 by Calmet, the action of the logarithm on a smooth radial function is given by this expression here, where gamma e is the Euler-Mascheroni constant. So here you see, for example, the presence of this logarithm of mu epsilon. So in principle, this term is infinite because we are sending epsilon to 0. But the idea is that also these integrals here, they will contain logarithm of mu epsilon. So when we take the difference, all the infinite contribution cancel out. So at the end, these give a finite result. So everything is finite at the end. So to solve the new equations, we consider small perturbation of order g squared. So we write the metric g mu nu. This is our solution as the known classical Rn metric, plus the things that we want to discover. So the quantum correction to the metric. And now we have to apply this into the equation of motions and solve them. And after that we do this, then we find this result. So first we say that this is the usual classical result for the metric, Reissner-Nordström metric. But then we have the new contributions, which are these ones. As you can see here, we have some terms proportional to g squared and with proportional to q squared. And then we have here the new terms. As one may wonder, why do we have here a nu here? So nu, as I said, is an arbitrary energy scale. So in principle, the metric should not depend on nu. But in fact, this is the case. So the idea is that C1, C2, and C3, they are renormalized constants, so they carry an explicit scale dependence, which is the following. So now if you plug these expressions for C1, C2, and C3 into these expressions of the metric, you see that the terms containing the mu cancel out. So at the end, the metric does not depend on mu, which is consistent because a metric should not depend on an arbitrary energy scale. Okay, so now we are ready to move to the correction to the entropy itself. Now, if we use the corrected metric, then we can determine the new position of the event horizon by solving the equation G of R equal to 0. We recall that for a classical RN black hole there are two horizons, but only the outer one is used to compute the entropy. And if we solve this equation up to order 2 squared, then we find this new radius. So this is the classical radius for a Reissner-Nordström metric up to order 2 squared, while this is the new contribution due to the quantum effects. So here, from now on, I will give the results, all the results up to order 2 squared, because as we know, astrophysical black holes have a very tiny charge. So the electric charge is not 0, but it is very small. So it is meaningful to give our results only up to order 2 squared, because other higher orders like Q3 or Q to the power 4, then they will be even more suppressed. And in the formula,
only 3 minutes left.
Okay, yeah. So the last ingredient for the Wald formula is the tensor, as we have seen before, and is the definition. So we have the square root of f divided by g with a minus sign. It's totally antisymmetric. If we use the Wald formula evaluated on the quantum corrected event horizon that we have found before, then we see this result. So the first term is the usual Hawking term, so the area divided by 4g, which is the classical result. Then we have this S0, which is the quantum correction to a Schwarzschild black hole, which is also the term which was found by Calmet. And then we have this term, this new term, which is the original result of this research. And the expression is the following. So we have this quite lengthy expression for this contribution to the entropy. And as you can see, for astrophysical black hole, these terms are suppressed. You see here we have 1 divided by m to the power 4. So the whole of this is suppressed compared to this one, because here we have 1 to the power m squared. And also, here we see that there is mu everywhere, but if we, as before, if we plug the definition of the coefficients, C2, C3, and so on, in terms of mu, then one can see that all the terms containing mu, they cancel out. So this is remarkable. So the entropy here is renormalization group invariant, so RG invariant. Namely, it does not depend on the arbitrary energy scale. So this is also a check that our results are indeed consistent. Okay, so let's see, to conclude, the possible future directions which stem from this work. So first, one could try to do the whole calculation up to a third order in curvature, since we did this to second order. Then one can ask if it is possible to reproduce S2s in some other methods. Or again, one can try to generalize these calculations. In this research, we dealt with Reissner-Nordström black holes, but one can do the same, generalize this to rotating black holes, because they are the most general black hole possible, astrophysical black hole. So they are black holes which have also an angular momentum. So the idea is to generalize these calculations for this new black hole. And finally, also one could have a look at the so-called ADS black holes, computing the quantum correction to the metric and entropy for this type of black holes. which, although they are not astrophysical, they are of particular interest in virtue of the ADS-CFT correspondence. So thank you very much for your attention.